works for the Austrian Academy of Sciences, and they will be presenting Gorilla, the guiding center orbit integration with local linearization approach.
Yeah, thanks first of all to give me the opportunity for especially FuseNet that I can present some of my stuff here. So the title of the Pecha Kucha is Gorilla as an acronym, but this is also the name of the computer code I wrote. So it's guiding center orbit integration with local linearization approach. So what is the guiding center approximation for charged particle orbits? In principle here, we don't follow the actual guiding center, which is a gyration in principle over the electromagnetic field, but instead we follow the guiding center, which can be more or less seen as an averaging over the gyro phase. But now we have very specific requirements to what we especially do. We want efficient box counting, we want physically correct long-term orbit dynamics, low sensitivity to noise in fields, and integrator efficiency. So we want to do that extremely fast. And why do we do this? Because our goal is that we want to model the distribution function that Dominic showed before in a kinetic way. And we do this with an approach we call the local linearization approach. That means we represent the electromagnetic field by piecewise functions. That means our technique is a mesh-based technique because electromagnetic fields are linear in 3D tetrahedral cells. And for those of you who are interested in mathematics, this can be considered as a quasi-geometric approach. So here we have the Hamiltonian formulation of the guiding center equations. And what we do differently, instead of taking the physical time t, we replace it with an orbit parameter tau that you can see here at the bottom. And the key point of our approximation comes now. What we are doing is we take the electromagnetic field quantities that you can see here at the top, and we represent them by piecewise linear functions. And if you do this in a smart way, you will obtain this equation set here, which is a linear ODE set. And this is extremely efficient to solve. And A and B are here constants. Now here you can see our 3D field aligned grid. So this is basically the mesh that I described before that is aligned to the electromagnetic field. And here on the right, you see how we split our space to obtain 3D tetrahedral cells. And this linear ODE set is then solved in one of those single cells. So how do we solve this linear ODE set? We have now our coefficients A and B, and they are constant inside such a single cells. That allows us to write the formal solution of this problem with this power series here. And this is exact if k goes to infinity, but it also allows us for truncating and giving approximate solutions. However, there are discontinuous coefficients. That means A and B that I showed before are discontinuous at those cell boundaries, meaning we have to compute orbit intersection with tetrahedral spaces whenever we follow our particle trajectories. Mathematically speaking, we have to solve this nonlinear problem here. Let's simplify the 3D problem just for illustration as a 2D triangle. We have our particle here at tau 0, it enters the cell, and we have to compute all intersections that represent this triangle, and the one that can be reached in the smallest positive time 1 here is the one we are looking for, our exit point. There are in principle 2 ways to solve this problem. A numerical approach with Runge-Kutta-4 in an iterative scheme also employing Newton's method, or an analytical polynomial scheme where we truncate the series from before and we obtain algebraic equations that can be solved with various solution orders then in the Larmor radius. Let's look now at some 2D results. Here you can see a Poincare plot. That means we follow the particle orbit in toroidal direction, and every time when we cross the phi equals 0 plane, we note this point. So what you see here in red, green, and blue are not lines, they are actual points that are very close together. And with this mesh that you can see in the background, we compare now an exact orbit result that is obtained without the mesh with a standard method and our Gorilla code in 2 different coordinate systems. And the results are indeed quite similar, but most important, they remain closed on the drift surface. So the canonical toroidal angular momentum is preserved. Now we also added axisymmetric electrostatic noise to the vector potential and the electrostatic potential up to 30%. Here the orbit shape is similar, but still they remain closed on the drift surface, which means this canonical toroidal angular momentum is even preserved under axisymmetric noise. We also applied this new integrator to stellarators, and here again Poincare projections, once in cylindrical coordinates and the same picture here in symmetry flux coordinates. The results are quite similar to an exact orbit, and they are getting better the higher the polynomial order is of our approximate solution. Finally, we also looked at the parallel adiabatic invariant, which is mainly almost conserved in stellarators. And that is true for third and fourth order polynomial series. But as you can see here, for the second order series, the Hamiltonian structure is violated. And on the right, you see this quantity, how it converges with a finer grid, so higher grid resolution. In the end, we applied this new trajectory integrated to a Monte Carlo model to compute transport coefficients, here D11. It was done with 10,000 test particles and the pitch angle scattering model with these normalization quantities. But what I want to show you is actually showing the results in comparison with an exact orbit integrator. Now on this picture, every line was obtained by exact orbit integration, and all markers were done with Gorilla. And you can see in all of these four pictures, the markers lie on the lines if you scan through collisionality or the electric field, or if you use electrons or ions. That means we get physically correct results. So finally, let me conclude. We have developed a computationally extremely efficient method. In our tests, it's up to 10 times faster than RK4 because we only solve this local linear ODE set, but still it's physically correct. So we preserve total energy, magnetic moment, and phase space volume. And this has this additional feature that it's also insensitive to noise. So with that, let me thank you for your attention. For anyone who's interested in the method we've developed, there's a paper coming out in Physics of Plasma in this edition in December. And also the Gorilla code is available on request. Just send me an email. Or also in addition, this Fortran code will be published on GitHub as soon as possible. Thank you very much.
Thank you very much, Michael, for the wonderful talk. Indeed, the Gorilla sounds quite catchy. Yeah, good job on that.